Okay, while we're waiting, several quick announcements. First of all, I'm still working hard on the grading. I should be done real soon. Finish number 4 already. I need to have to transfer what I got it to Canvas. And I've posted a quiz number 8 and set up a new due date. It will be next Wednesday. And supposedly it should be a fairly painless quiz because we have talked about it, how to design shear for given apply shear forces in previous lectures. So you can refer to that one and finish that one. And we'll not talk about the correct solution since the due date is Wednesday, so give us more time to think about it. But we will show the correct solutions, and that one may be posted before the exam, so you have something to go by. But that's additional example already. So that's about the quiz number 8. And regarding to the progress, we have talked about the slab now, and we will finish the slab this week, and a little bit maybe after you come back and break on Monday. But most likely we'll finish all the information you needed for the exam number 2. All right. So I think next week is spring break, or the week. I think so. Next week is spring break. So let me just go ahead lay out the content that we cover in exam number 2, so get head start. So for the exam number 2, you'll be mainly tested on the irregular sections. We talk about how do we compute the flexure resistance or flexure strength of the irregular section. That means the section with openings and duct and all that. Okay, so there at least one problem on that, and we'll talk about the shear, and that's the most important thing. We may have 2 problems regarding shear. All right, we may have 2 problems regarding shear. Of course, I forgot to mention the entire layout or format is similarly to exam number 1. We have first one multiple choices, and number 2 and number 3 are fully worked out the problem. I have already designed the exam already, and the exam looks quite different. I have added new problem since last semester we didn't cover the speed as we had this semester, so it will be entirely new exam. Okay, now for exam 2, problem number 2, number 3, like I said, we might have 2 shear problems. Okay, now in terms of shear problem, you will be tested on how to design for spacing. That means the stirrup size will be given to you. All right, the stirrup size will be given to you, and I will run a review session. Excuse me. I will run a review session the Monday in that week, the Monday before April the 1st. Okay, so if you have time over the spring break, I strongly suggest you go over the content and get ready for the exam. All right, and again, there's 3 hours like before, and it's going to be scheduled on April the 1st afternoon, 1 o'clock to 4 o'clock. Okay, all right, so I'm just going to pause for a second. Any question for the exam number 2?
Does the content correlate to any chapters at all? Like, can you point to like chapters 6, 7, 8, or something like that that we can look at?
Yeah, it should be in the shear, so I suppose be chapter 6. And one-way slab should be in chapter 4 and 5. Okay, I may misread the chapter name, so I will confirm that afterwards and send you guys an email about it. But for the exam, I think the most important thing is lecture notes. So you really want to go over the 2 example problems that we show on how to calculate shear spacings for the stirrups. All right, any other questions for me on exam number 2? All right, so we have provided makeup exam for number 1. Most likely we will not have makeup for exam number 2. All right, so for some of you who are thinking about banking on having a makeup if you tank for the first try for the exam number 2, I don't think that's going to happen. All right, we will not have makeup exam for number 2. Okay. All right, well, if there are no further questions, I'm just going to resume on talking about the one-way slab, okay? Resume talking about one-way slab. So first I'm going to share my screen. And one-way slab will be in exam number 2, I forgot to mention, but will not be in terms of major problem like full workout problem. Will be fill in the blank and multiple choices. But still, I'll show you how easy or how simple the one-way slab design is actually is. So you have to go through the one-way slab whole process regardless. Okay. All right. So where we stopped last time, we introduced the one-way slab, right? Again, review what is the definition of one-way slab, meaning the moment, right, is along one direction or the slab bends in one direction, so-called one-way slab. And the definition of that is the transverse span, which means the span in perpendicular to the bending direction is 2 times or greater than that of the span length when they have a bending moment, right? And the reason why we're so interested in one-way slab is that there are also a two-way slab. The difference between them two is that the moment distribution is different. For one-way slab, we can divide the moment on the beam by regions, right? So two ends of it will have the negative bending moment, and the one end of it will have the positive bending, or middle of it will have the positive bending moment, right? But for the two-way slab, you see the right-hand side where we have this more like a circle or enclosed shape, where in the middle portion of it, we have the positive, and outside we have the negative. All right. So it is crucial to understand how moment is distributed in the slab so we can design for it. Right. So that's also about the definition of one slab. And here's a detailed drawing how the one-way slab looks like, right? So we have a span length in L1 direction, and we have the transfer direction L2. And we showed you guys it is a unit strip that we're interested in, means 1 foot of a width that we're interested. Okay, so whenever we're talking about one-way slab, we always take 1 foot of a width of the slab for the design, right? And then we also showed you that we might have positive and negative bending moment, depends where we're at, and bars are a little bit different at different locations, right? And we introduced a concept called reinforcement for one-way slab, right? And this is slightly different. We said AS per foot, that is the reinforcement provided in the one-way slab per foot, equal to AB multiplied by 12-inch per spacing S. Then last time I think I left there, and this right here, let me be more specific. This is the area of a single bar. Okay, this is the area of a single bar. Okay, what does it mean, right? What does it mean? Now I have shown you how to do the splice, so I'm just going to take this one out since it's not related to one-way slab here. Okay, cut. All right, so come back to this. What does it mean, right? It means that if I have a bar like this, and then I have, or I should use dashed lines here indicating this is the unit strip per 1 foot. Oops. Per 1 foot. Okay, unit strip per 1 foot. All right, and then also you think of it, you actually have a continuous slab in the transverse direction. All right, this is in the L2 direction, by the way. Okay, this is in the L2 direction. So naturally, you have another bar adjacent to it. All right, and usually what we control is we do not control the bar size. You know, usually these bar sizes are given, so we have control the spacing. Have control the spacing. So on the left-hand side, this is the actual scenario. Okay, this is actual configuration when you put the bars in. So all this equation does is a conversion, that you want to convert this into a 1 foot unit strip with an AS per foot. All right, so this single bar area, for example, if it's number 9, ETC, or like EG, for example, for number 9 bars, AB would equal to 1 inch squared. Okay, usually it won't be number 9. Let's just be more careful. Is number 3, 11, because usually that's what we select for slabs, number 3 or number 2s. Okay, something like that. This is the single bar. Okay, let me just be more clear. Single bar cross-section area. Okay, Essentially is that we are similarly like we did for shear, we are designing for the spacing. Okay, that is we're designing for. That is we're designing for. Okay, so there's a conversion, essentially. There's a conversion to convert a known bar size with a spacing that you have control over to convert into an area per foot. To convert into an area per foot. All right, so that is the conversion. That is the conversion. All right, any question about this? Any question about this? Okay, so this is very critical. Okay, we need to understand how to do this. All right, so with that, we're gonna move into the actual design. We're gonna move into the actual design, right? So now let's talk about it. So design for one-way slab, usually when we talk about design for one-way slab, is designed for reinforcement. Design for reinforcement. Okay. Okay, and to be more
Is that
specific.
supposed to say one web or one way?
Oh, sorry, one way. Thank you. Okay, one-way slab is designed for reinforcement or more specifically for spacing. Okay, or in this case, we call it known bar size. Known bar size. That is, you are given the bar and you know the size and you just have to provide the spacing for it. Okay, so how do we design for it? How do we design for it? There are two critical criterions. Very important, two criteria. Number one is that we need to design for reinforcement, right? That required by flexure strength. That means bending, all right? That means bending. So you have to provide a reinforcement spacing, right? Meaning spacing for bending, right? Like we did for the normal flexure beams design, right? And the other thing we have to design for is a reinforcement required. This is new, okay, folks? This is new, okay? Required by temperature and shrinkage. Temperature and shrinkage. Okay, this is new. This is new. So why temperature and shrinkage? Just because a slab is such a shallow sections, and hair crack will affect its serviceability in terms of deflection. All right. So when the deflection is called in check, we have problem. Okay. So these are the main criteria, but there are also other sub criterions. Okay, there are sub criterions, and these are quite important as well, but they're not the main design criteria, meaning you don't have to do a whole lot of calculation for it. Now, the first one, let me just somehow, let's use S1 here. First one is deflection control. Deflection control means you have to control the spacing, right, of the reinforcement to ensure that you have sufficient reinforcement to maintain the stiffness of the section. All right, so that means you cannot put the spacing of the flexure reinforcement, right, bigger than this max, and this max distance is the smaller of the two. What are the smaller of the two? 3 times HF, that is 3 times the height of the slab. All right, and if this is the slab and this is cross section, and so HF is this right here. Okay, 3 times HF or 18 inches, and you can find this in ACI. Can find this in the ACI 7.7.2.3. Okay, so that is the deflection control. And number 2 sub criterion is crack control spacing. Also very important, crack control. Again, it's always in terms of a spacing, right, between the flexure reinforcement. And this spacing is designated or defined as smaller of the two equations here. That is 15, okay, 40,000 divided by Fs. Fs is the stress in the bar, and I'll explain, okay? Multiply 2.5 times of Cc. Okay, now this is the concrete clear cover. Now we have talked about this in a previous lecture when we talk about bar spacing, but let me just be more specific, okay? When we talk about concrete clear cover, right? We mean literally between the edge of the bar to the edge of the concrete. So this is CC, all right? And we haven't talked about this yet, but let's talk about it, right? And the other equation is 12 multiplied by 40,000 divided by FS again, okay? Now, this is the first time you encounter FS, okay? FS is called, definition of that is called the surface stress in a bar. What I mean by surface stress, now we all know that when the beam fails, when the beam fails, right, you will reach the yield strength of the bar. However, in service, right, this stress is estimated only to be 2/3 of the yield strength. Okay, 2/3 of yield strength. So this is the surface stress in the bar, and we use that to determine the maximum spacing for crack. Maximum spacing for cracked. Okay. All right. So this gets a little bit complicated. This gets a little bit complicated. You see that we have so many things to worry. We have so many things to worry. We have to worry about the reinforcement required by the flexure strength, which means the bending moment. Have to worry about reinforcement required by temperature shrinkages. And have to worry about the deflection control, crack control. There's so many things we have to design for. So how to design it? How to design it? So here is a table. Here's a table. Okay. So design table for one-way slab. Okay. We can simply divide them into two sections. That is one, design for longitudinal direction, right? Longitudinal direction. That means this is in L1. This is in L1. Okay, so let me show you more clearly, hopefully through a drawing, right? So imagine you have a one-way slab that is poured integrally with the beam like this. This is side view, and this is one-way slab, and I'm just gonna cap it here. Okay, and now we say this is L1, right? This is L1. Of course, you have column underneath it, right? To support. Column underneath it to support it. Something, or this is more like a wall to support it, something like that. And so this is L1 direction, and this is L2 direction, okay? And you know that this is the bending direction. So in terms of reinforcement, I want you to think of this way. So the slab here, and let me use the color blue. Okay? So inside, you see, you have reinforcement like that, right? Along the L1 direction, Okay. We call this the flexure reinforcement. Okay, we call this the flexure reinforcement. Okay, this is section 1. Okay, longitudinal direction means flexure reinforcement. Okay, for this, right? And we said, usually the bar size is given, is normally often given, and forgive my chicken claw write up on this iPad thing, but usually AB is given. All we are asking you guys to find out is the spacing between them, right? Spacing between them. This is what we're designing for. Is the spacing, right? So in this scenario, okay, I'm gonna go ahead, call it S1, and 1 representing flexure, meaning this direction, right? Spacing in this direction. So it means it is the smallest of, okay, smallest of following. So first of all, it is first equation AB means the single area, right? Single bar area multiplied by 12, and this 12 is conversion, right? 12 inch per foot, conversion factor, okay? 12 inch per foot divided by the required AS per foot. And AS per foot is the converted, right? Is the converted. And I explain how does that relate to the moment, okay? But all you need to know right now, it is related to the moment. And let's say MU here. Okay, related to the moment MU here. All right, so this is the first equation. And then it has to be 3 HF or 18 inches. And remember, this is so-called the deflection controlled criteria sub. Right? This is deflection controlled criteria sub. And then the last two equations are the cracking that I have shown you. 40,000, okay, 440 after the number, okay, 40,000 divided by Fs minus 2.5 concrete clear cover CC, and this is 12, and I have a 40,000 again at the top divided by Fs, okay, and you know this is crack control. All right, this is crack control. Okay, so this, ladies and gentlemen, right, is the is the spacing for flexure reinforcement. Okay, but don't forget, even if you satisfy all this, you have to make sure AS per foot provided. AS per foot provided. Okay, provided has to be bigger or equal to AS per foot provided, minimum. And that, ladies and gentlemen, is an equation of 0.002 AG in ACI. Okay, you might not have this, okay? It's in a revision, ACI revision R 10.5.4, but you don't have to really worry about that. You just need to remember this equation 0.0, okay? I want to emphasize 0.002 AG. Now, what is AG? AG is the cross-section area, right? That is B width multiplied by HF, and B in this case equal to 12 inch. 12 inch. All right. So now this is the first row in the table is how we design for the longitudinal direction. Okay, and don't worry, I will show you an example, right? But this is how we design for longitudinal direction. For transverse direction, okay? So transverse direction is a little bit different, okay? So how different? All right, so let me borrow this figure again. Let me borrow this, okay? All right, let me borrow this. I probably don't need this, so I'll just carefully copy this and paste it here. Okay, okay. So for this, right, so I say this is for shrinkage and temperature. Now we haven't touched yet. So shrinkage and temperature. Okay, reinforcement. Now this is different from the flexure. This is different from the flexure. Okay, why so is that we said, previously, these blues are the flexure reinforcement, right? So shrinkage temperature is different. Shrinkage temperature is in the other direction. In the other direction, that means I have bars. And ladies and gentlemen, just be careful, right? Just you see that I did not put the bars into the web, okay? Did not put the bars into the web. The reason is that they're not for the beam. They're not for the beam gooder in that direction. They're only for the web. They're only for the slab, okay? So I only put it into the slab. Okay, this is also can be treated as part of slab, that's fine, but you see, this only in the slab, has nothing to do with the beam in the transfer direction, okay? Has nothing to do with the beam in the transfer directions, okay? You gotta understand this, all right? I don't want you to put in the bars in the bottom of that gooder and say that, look, Bob, that's my flexure, that's my shrinkage, and I'm gonna go bananas, okay? All right, so this is the transfer direction, okay? So now these are the shrinkage. These are the shrinkage plus temperature reinforcement. Okay, shrinkage and temperature reinforcement. All right. Then again, we also make sure that, of course, this is along L2, right? Along L2. And we make sure that the provided reinforcement, right? For shrinkage and temperature, let's, instead of spacing, we will design for the minimum, right? Minimum, okay? And be careful, right? This minimum, right? Let me just move it here. Will be compared to the provided, which is AS per foot provided, okay? Has to be greater than or equal to AS minimum. And we're not talking about spacing anymore for shrinkage and temperature, right? For shrinkage and temperature, we're not talking about the spacing anymore. So this minimum, okay, AS min, is a little bit complicated. It's a little bit complicated. Okay, so how complicated? Here you go, right? This minimum equal to a largest, or a spacing, smallest, area, largest, right? Largest of these three, right? First of all, 0.002 AG, and same definition as previously AG, okay? But has a little bit condition. This is for Fy smaller, or let's say 40 or 50 KSI for low yield strengths of bars, okay? 40 or 50 KSI. Let me zoom in so it will be easier for me to write, okay? 40 to 50 KSI, and it is 0.0018 AG bracket for Fy yield strength is equal to 60 KSI. Very precise, all right? Very precise. And also this is 0.0018 60,000, okay, divided by Fy, 60,000 divided by Fy bracket Ag, okay, and this condition is for Fy greater than 60 KSI. Very specific, okay, very specific. All right, so that is the reinforcement, but not all this, right? AS min has to be, sorry, AS provided has to be color coded, right? I saw the question, Lane, just give me 1 second, I'll answer that, okay? I have to also satisfy that AS per foot provided has to be greater or equal to 0.0014 AG, okay, 0.0014 AG for, this is the case, okay, for Fy is greater than 60 KSI. Okay, so a little bit messy here, but that's what the code says. Okay, that's what the code says. All right, so you want to make sure that you understand the shrinkage and temperature reinforcement is different when you talk about design than the longitudinal direction for flexure, okay? And we will also showcase that, the difference between them, okay? Showcase the difference between them. And they are both, the shrinkage and the flexure, they are perpendicular to each other, right? They're not in the same direction, all right? Okay, so the bars, question from Lane, the bars still required directly above the web. I realize they're needed for shrinkage rather than supporting the weight. That's exactly right. For the one-way slab, the main purpose we're saying they're one-way is that we only have to worry about their bending or their soft weight and dead weight in the L1 direction. And that's why we calculate the spacing based on the subjective moment along the L1 direction. All right, that means the other direction, transverse direction, they don't have to carry any load. The meaning of the shrinkage and temperature reinforcement is mainly for freeze and thaws and support expansions and all that, right? Crackings and all that. So these are not structural reinforcement in a sense. Shrinkage and temperature, they're not structural reinforcement in a sense. They're more like a service reinforcement. Okay, hence it is more simpler, or this is simpler to design it for the shrinkage and temperature. You just have to follow the code and you don't have to really calculate too much about it. All right. Okay. Now, why am I going extremely slow? Because this is very, very important. We will have multiple choice and fill in the blank for this in the exam number 2, okay? And I see a lot of students missed out. I see a lot of students missed out, okay? Anyway, let me quickly go on, right? Quickly go on. So I want to show you an example. I want to show you an example, right? So all this said and done, let's put it into practice, right? Design one-way slab, design one-way slab, okay, as shown. Okay, as shown. So here, I'm just gonna draw my simplified drawings, right? Draw a simplified drawing. I say I have a segment of one-way slab, and I have a span length of L1, and I have a span length of L2. Okay, and to put it even the simpler form, I'm just say, look, essentially that is a simply supported beam. Okay, I'm gonna assume it's simply supported, which in the real cases now we'll talk about next lecture. But anyway, let's assume simply supported. Okay, and then we have a distributed load on top. Distributed load on top. Okay, these are the distributed load, and we say the applied distributed load omega u equal to 315 pound per square foot. Okay, a later trick here for you. Okay, in case you didn't see, it's a pound per square foot. Okay, pound per square foot. And now I have a simply supported span length that is 10 feet. Okay, all right, so let's list some of the parameters. The dead load is self-weight only. Okay, I still have dead load, right? I have dead load on top of it, just like any other structures I have to compute for cross section, which I will show how to do that, right? I have a live load, right, equal to 150 pound per square foot, okay? And I already write here, right? So I will show you how I got this number, right? I will show you how I got this number from these two, okay? But you should know that this is where it is coming from, okay? But I'll explain to you, okay? Now, the compressive strength of the concrete F prime C equal to 4 KSI, all right? And let's say the yield strength, and be careful, okay? The yield strength of the bars for flexure or for shrinkage is 40 KSI, okay? Very low, okay? So this is our design problem. All right, so first of all, I have a dimension of the slab HF, all right? And I also need to design it for a unit strip, remember? Unit strip, and that is 1 foot right here, 1 foot right here. Okay, before I start, right? So let's say design, before I start, first thing is estimate the height of slab. Okay, you say, whoa, Bob, stop right here. You haven't talked to us about how to estimate the height. You're gonna pull us down again, like in exam number 1, just ask us straight to give you the height. No, I won't. As a matter of fact, I showed you how to estimate height for the beam. So here is how we estimate the height for the slab, okay? And this is based on ACI 9.3.1, okay? 9.3.1. All right, so you don't have to work a whole lot about it. Just remember this equation. So HF, okay, by definition is roughly here estimated as L1, right? L1 divided by, I hate to do this because every time I use that, some people ask me what. L1 divided by 20, okay? And 20 is just a factor, all right? It has nothing to do with it. And multiplied by a 0.4, plus Fy, which is the yield strength of bar provided to the slab, divided by 10,000. Okay, sorry, 100,000, not 10,000. 100,000, basically 100 KSI, okay? 100,000 and bracket. All right, so this is just the equation. All I'm saying is you remember this equation, okay? Remember the equation, okay? And the meaning of this equation is actually just a normalized number. So bring the number in. So L1, what is L1? 10 feet. So 10 feet. I want to convert into inches, okay? Because this has got to be in the unit of inches, okay? 12 inch per foot. And you see a lot of units along the course of this slab design because we will need it. Okay, we'll need it, and I'll go through that. Okay, very important for slab. And this is 0.4 and unitless. Okay, unitless plus Fy. I have what I have 40,000 psi. Okay, unit here. Okay, unit here. So this is 100,000, basically also psi. Okay, psi. Okay, so this canceled. I have a unitless number here, 0.4 plus 0.4, 0.8. So HF equaled, I got this one here to be 6 multiplied 0.8, about 4.8 inch. And that is the height estimated for the slab. So first thing first, before I even do anything, I say, you know, my height, HF, has to be 4.8 inches. Okay. Matter of fact, if I want to be more precise, and you don't have to change your equation, just add on to it. So it has to be greater than or equal to, greater than or equal to, greater than or equal to this 4.8 inches. Okay. Of course, you don't want to be too high, too tall, because you lose the structure height. So if for a parking garage, that's where usually one-way slab is at, you might have a problem running into the ceiling. Okay. So in this case, we'll say use the height of the slab to be 5 inch. Slightly higher than that. Okay. Slightly higher than that. So with this estimation, I can start looking at my slab. All right. And the way I do is, first of all, is 1 foot unit strip. Okay. Always 1 foot unit strip. All right. And I know my total height is HF equal to 5 inch. How do I know? I estimate it. And I have a bar here underneath it. And you remember when we talk about bar, this is single bar. Okay. So naturally you start saying this is AB. AB, single bar, 1 bar. Okay. All right. So here is another new thing for you. Okay. There's another new thing for you. Now for one-way slab. Okay. For one-way slab only. Okay. Now 2 ways, only one-way slab. Okay. The depth, right? In this case, the depth is D, right? Roughly equal to what? Equal to the height, HF, minus CC, concrete clear cover, right? And that clear cover is really from the edge of the bar to the surface of the concrete here, minus bar size, which is dB, divided by 2, right? Well, what we have here in the depth, D, roughly equal to what? 5 inch, okay? Minus, what is CC? And again, this is the little bit important for us. So I want to put in 7.5 inch. When you don't know it, you can assume 0.75 inch. All right, just make assumption here, 0.75 inch. Why this is important? Because in exam, I want you to use this number instead, okay? And minus 0.5 inch. And you may ask, Bob, didn't you say that the clear cover depend on the weather condition exposure? Yes, usually one-way slab will not be exposed directly to the weather. It's going to be indoors. So we can use this number constant, okay? So in your design life, unless otherwise, use this. And the reason why I emphasize this, you realize later, is this very thin of clear cover. Some people may argue, may have some corrosion problem, but because we always have a height restriction where we put in the one-way slab, usually parking garage or residential buildings. So this is just a normal practice, okay? I just want you to know that. All right. Anyway, so you see that immediately I put in the 0.5 inch. Why is that? Because here, again, this is old assumption. That's why I use red. You can assume number 4 bars for flexure for one-way slab. Whoa, that's very small, way smaller than the flexure beam. Yes, indeed. But usually we use number 3 and number 4. Number 4 is very commonly used, okay? So number 4 is preferred. All right? Okay, so this part is very critical. All right, but now this is when everything is kind of known, I will just put a blunt word here. If unknown, which means nothing is given, you can assume, all right, you can assume D equal to a 0.95 of HF. Sorry, let me remove this equal sign and replace that with the approximate sign, okay? 0.95 HF. I keep emphasizing, you realize that I keep emphasizing you want to keep a small, clear cover, right? So you gain a lot of depth out of the HF. All right, you have to efficiently use the section to give you that lever arm to resist the bending moment, okay? So that is critical. So this is 95%, which is pretty high, okay? Pretty high. Okay, so anyway, at this point, we can do a summary here saying, okay, now after all this assumption, 5 inch of a height, right? And depth is 4 inch. What's the fuzz, right? You just got this number and number 4 bar, right? No big deal, right? This is what we end up with at the first step, right? You see, I almost got all the critical information in the first step by estimating the height and utilize my design knowledge for it. So that's all I have to go on, okay? Second is to find out U and AS per foot required, okay? AS per foot required, okay? So how do I do that? First of all, what is the dead load? The dead load is a slab weight, right? And be careful, we're talking about per foot. We're talking about per foot. Why per foot? Because, this is the design unit strip that we're looking at is per foot. Sorry, design unit strip looking at per foot. So to do that, right? So we're looking at a section like this, this is 1 foot and this is HF. Now you remember, right? When we do the self-weight, we're essentially using the cross-section area for the slab. So what we do is HF multiplied by 1 foot, right? That's the area unit strip, remember? And multiplied by 150 pound per square foot. Where that coming from? That is the concrete, remember? Sorry, per cubic foot, okay? This is per cubic foot. This is the concrete, okay? Self-weight, density for concrete. And this is looking good, right? But I want everything converted to by foot, okay? So watch me here. This is HF, right? What is HF? HF is a 5 inch, okay? 5 inch. And this is pound, right? So I have a 1 foot, so 12 inch, okay? 12 inch, right? I have 2 inches now. Now look here, I have 150 pounds, so LBF divided by what? Divided by 12 inch. This is cubic, okay? Multiply 12 inch, multiply 12 inch. Okay, so I have inch, 3 inches. All right, so now I end up with, let me put the unit straight. So this is 5, this is 12, this is 60, and multiply 150, and I have inch squared, check, multiply pound, check, and I have a 12, 12, 12, so 12 to the power of 3, and inch. Okay, so inch to the power of 3, right? You can leave left as that, that's fine, and then cancel that, remove that, I have pound per inch. All right, pound per inch. So now, okay, right, I want to convert this to be 60 multiplied by 150 and divided by 12 to the power of 3, okay? And I say I want to convert this to be a pound per foot, right? So pound per foot, I have to multiply 12, and here's I convert it back to pound per foot. Okay, pound per foot. How do I do that, right? There's inch, I just convert to a foot and multiply 12, right? So these are gone, and these are 2 here, right? And this, ladies and gentlemen, very important stuff. I got 62.5. Then this is pound, and this is foot squared. Sorry, pound per linear foot. Pound per linear foot. Okay. All right, so be careful on this unit, okay? Be careful on this unit. All right, and this is only the dead load. This is only the dead load. All right, why am I playing so much? Well, you get it later, okay? You get it later. Sorry, squared, okay? Not per foot, square, okay? All right, so this is 62.5 pound per feet squared, okay? Now, Omega U is the applied load, and that is 1.2 dead plus 1.6 live. Okay, so I have 1.2 multiplied by 62.5 plus 1.6 multiplied by 150. Where did I get this number? This is given. Okay, just want to confirm that this is given. Okay, 150 pounds per square foot. So I got this number to be finally a 315 pound per square foot. Okay, I'm paying extra attention to my unit. Okay, and I'll show you why it's so important later. Okay, I'll show you why this is so important later. All right. Okay, now I have my applied loading, right? That is 315 pounds per square foot. I'm pretty happy about it. I'm pretty happy about it. Okay, so I'm gonna go design, right? I'm gonna go design, but before I do that, I can calculate my applied moment or factor moment MU here. The MU for simply supported beam, simply supported, I can use that equation omega UL1 squared divided by 8. Okay, so to convert everything by kips, this is 0.315 kips, right, per square foot. Okay, and multiply by 10 feet squared divided by 8, and I got this number to be a 394 kips. Okay, foot. Okay, kips foot. Right? Usually you stop there. You say, look, let's apply moment and move on, continue to do the calculation needed. But be careful. This is whole thing we're talking about is per one, remember, per the slab, which is HF, and this is 1 foot of a unit strip. So don't forget, this is per foot. All right, and this unit here, I cannot emphasize enough, is very weird. Okay, it's very weird, but I want you to remember this is the unit. Okay, don't get it wrong. So MU here, let me rewrite in red. MU here is 3.94, and the unit is kip dot foot per foot. Some of you say, Bob, look, kip foot divided by foot. Why don't you just cancel that, right? Why don't you just cancel the foot? No, I will not, because I want to remind myself that I'm working on a per foot slab right here. Okay, this is where this is coming from. I want to remind myself that I'm working with respect to a per foot unit strip here. Okay. All right, so this is what we're looking at is this is MU, right? Applied moment. How to do from there, right? I have 2 minutes, just spare me 1 second, okay? So with this, things become easier. So I'm just say, okay, MN, which is the nominal moment, right? Phi MN has to be greater than or equal to MU, isn't it, right? Isn't it? So I can have my AS, right? So MN equal to MU or greater or equal to MU divided by phi. So the required AS per foot, okay? Required AS per foot should equal to MU divided by phi, okay? Fy d minus half A, remember? Old friend, flexure design, okay? Old friend, flexure design. But in this case, we can assume phi equal to 0.9, and also we can assume d minus half A for now equal to a 0.95 d. Okay, 0.95 d. That's another assumption of a shallow slab design. Okay, very critical. All right. Okay, I'm gonna stop right here. This is a good stop. And next lecture, which is tomorrow, will show you how to complete this flexure design. Okay. If you have any question, welcome to stay behind and we can talk about it. Okay. Thank you very much and see you tomorrow.
Professor.
Yeah.